Hello everyone, welcome to this session on modernizing your monolith using the Strangler pattern. First off, I just want to say that I really appreciate you taking the time to watch this session. My name is Anita Dinadayalan. I'm a developer specialist solutions architect here at AWS and I'm based out of Singapore. I work for the developer acceleration DevAx team. In our team, we accelerate our customers to build secure, reliable and scalable modern applications on AWS. You probably want to know what you can learn from this session today. Today, I'll discuss the Strangler pattern in the context of an e-commerce application, Storefront. Storefront is a monolithic application, typical three-tier with a web layer, an application layer, and a relational database. Monolithic applications have most of their functionality within a single process or container. Internally, they can have multiple components, layers, and libraries. Storefront application is running on AWS. It's deployed on an EC2 instance with an Amazon RDS database. An S3 bucket stores the static assets like HTML, CSS, JavaScript, etc. The products sold by Storefront have recently become extremely popular. The application has been struggling to scale to the load. They have set up auto-scaling of the EC2 instances, but they are not able to scale the individual functions. So if they want to scale the order service, there is no way to scale just that one service. The entire application has to be scaled to cater to the incoming requests. The user interface hangs every day during peak hours. The relational database can only handle so many transactions per second, and this is limiting the platform teams from doing any further application scaling. Database contention also occurs during peak hours. When releasing changes, the entire application has to be regression tested and released to ensure application stability, and this is increasing their cycle time. The Storefront product team is struggling to cater to the new business requirements as maintaining the monolithic application is taking most of their time. Now seemingly technical issues like UX slowness and database contention manifest in real business problems. Storefront's IT team is still dedicating majority of their resources in keeping the lights on. 80% of the developers' time is spent on operations and maintenance and only 20% on innovation. Technical issues result in long release cycles, loss of productivity, and loss of customer trust by not complying to regulations on time. Like most organizations, Storefront wants to reverse the 80-20 ratio. They want to spend 80% of their time on innovation and 20% on operations. Innovation and staying ahead in the market is their top priority now. They also want to reduce their total cost of ownership and scale their services based on demand. They also want to integrate security into every stage in their design. Storefront IT team understands the benefit of modern architecture and has decided to modernize the monolith into microservices architecture. With a microservices architecture, the monolithic application can be split into smaller components. These components can scale independently, they can be released independently, and each of these services can be owned by individual teams. So it's a lot easier to have a higher velocity of change. The blast radius for changes will be smaller as the services will be loosely coupled in the microservices architectures. The application can also scale quickly to potentially millions of users, manage petabytes if not exabytes of data, and respond in milliseconds, solving the UX and database contention issues. But Storefront is a business critical application and they do not want the customers to get affected during the migration. They want to reduce the business disruption during the migration. They can consider going in for a big bang migration into microservices architecture. But as Martin Fowler rightly said, the only thing a big bang rewrite guarantees is a big bang explosion. So the alternative is to migrate the monolith gradually into microservices architecture to reduce the transformation risk and disruption. The solution here is to use the Strangler Fig pattern. By the way, in 2019, Martin Fowler decided to call the Strangler pattern as Strangler Fig pattern to reinforce the metaphorical link to the Strangler fig trees in Queensland coast. This pattern involves moving microservices gradually by extracting the features and creating a new application around the existing system. Application users will be able to use the newly migrated features progressively. When all the features are moved out, then the monolithic application can be decommissioned safely. I'll now take you through how you can migrate the microservices architecture using the Strangler pattern. This is the storefront application again. Before the actual migration, you need to first identify the microservices from the monolith. When identifying the microservices, you can look for natural divisions between service classes. Many of these will have their own data access object and will peel easily. Services with some related business logic are good candidates. You can also look for classes with no or few dependencies. You should also try to refactor some code to clean up any cobwebs. Alternatively, one of the key tools we have is domain-driven design, commonly referred to as DDD. Domain-driven design aligns well with the characteristics of microservices, encapsulated, defined interfaces, and isolated. DDD gives us a framework to make decisions about domain boundaries. Identifying domains and domain boundaries within the monolith is important to break it down into microservices architectures. Domains once identified are suitable for breaking into their own microservices. DDD also provides a common vocabulary called ubiquitous language to discuss with our technical teams and business owners. Using DDD and ubiquitous language, we have a way to identify the domains and their boundaries. Bounded context is a central pattern in domain-driven design. It is the focus of DDD's strategic design section, which is all about dealing with large models and teams. DDD deals with large models by dividing them into different bounded contexts and being explicit about their relationships. A bounded context encapsulates a single domain and defines the integration points with other domains. Microservices should have a well-defined bounded context and should do just one thing. Here you are actually saying two bounded contexts, sales and support. The sales context can become a microservice and the support context can become another microservice. Apart from using DDD, you should also consider the compliance requirements, speed of release, the geographical location of teams, scaling needs, use case driven technology needs, and of course the cognitive load of the teams when identifying the microservices. Here the cognitive load is very important. If the system of microservice is too big to reason with, it should be split. Software that is too big for our heads works against organizational agility. Cognitive load on the team reduces their effectiveness and should be considered while breaking down a monolith. In 1998, psychologist John Swiller defined the term cognitive load to mean the total amount of mental effort being used in the working memory. And he identified three kinds of cognitive loads: intrinsic, extraneous, and germane. Intrinsic refers to the skills that are required on a day-to-day basis. This can be driving, or it can be the knowledge of defining classes in a programming language. Extraneous are the distractions, the activities we want to minimize. This can be undifferentiated heavy lifting tasks like manual release processes that bring down productivity. Germane is the knowledge of the domain. We need the team to have most focus on this. When the microservice is at an optimal size and can be reasoned with by the team, this will help them focus on the domain-specific requirements and increase productivity. Now the application team, they have identified three main features in the storefront monolithic application: the order feature, inventory feature, and the cart feature, and all sharing the same database. The order and cart features internally call the inventory feature for item availability and checkout. Now while storefront team is planning the migration, a request for a new feature arrives. What can you do here? Should you add the new feature to the existing monolith? Here the best approach is to implement the functionality as a new microservice and freeze changes to the new changes in the monolithic code base. At the same time, bug fixes should still be allowed on the monolithic application. The new microservice will have its own data store. Now the team decides to migrate the inventory feature first into a new microservice. If you see here, the order and the cart features call the inventory feature. So when the service is migrated out, order and cart features should still be able to call the inventory microservice without any code changes. So the solution is to use the anti-corruption layer. The interface of the newly migrated inventory microservice may or may not match the original inventory features interface. So in order for the order and cart to call the inventory microservice transparently, an adapter or facade layer should be implemented. This is called the anti-corruption layer. The order and cart features will still call the skeleton of the inventory feature inside the monolith, and the call will be routed to the inventory microservice through this anti-corruption layer. You may wonder why the order feature cannot call the inventory microservice directly. You should remember that we are trying to reduce regression and business disruption here. So we do not want to amend the implementation of the order feature. Order feature should still call the inventory feature without being aware of the microservice migration. This loose coupling is required to reduce the regression issues. The strangled architecture would look like above in the intermediate state. The inventory service is implemented using a Lambda function here, and it uses an Amazon RDS database. Order and cart features are still in the monolithic application deployed on an EC2 instance. Now that the inventory microservice has been migrated out and it stores data in a separate data store, but the existing monolithic database is still being used by the monolithic application. If there are any downstream dependencies, the inventory data should be synchronized for the time being. So the storefront team introduced a synchronizing agent in between the inventory service and the monolithic database. The inventory microservice sends an event to the queue whenever the inventory database is updated. The synchronizing agent listens to the queue and continuously updates the monolithic database. The data in the monolithic database will be eventually consistent for the time being, and the storefront team have to set an expectation of the application users on this. Next, the order feature has been migrated into a microservice. Now the order microservice can call the inventory microservice directly. The anti-corruption layer will still remain as the cart feature is not migrated yet, and it's required to call the inventory service. Here the order service is implemented using another Lambda function, and it uses a DynamoDB database. The cart feature still exists within the monolith. The end user is not aware that the call is being routed to a microservice, and there is minimal disruption for the customers. Finally, the cart feature is migrated and the anti-corruption layer can be removed. Now the monolith does not have any functionality and it can be safely decommissioned. This will be the final strangled state with the monolith decommissioned. The newly strangled architecture now has 3 microservices, each with their own individual databases. If you can see, each service uses a different type of database as required by the use case. Here, when order service Lambda scales on demand, Amazon DynamoDB database scales accordingly, providing millisecond response times and connections for millions of users. This concept of using purpose-built databases for use case specific needs is called polyglot persistence. The Lambda functions themselves can be implemented in different programming languages as required by the use case. The original architecture exposed database contention issues due to the limited size of the relational database's connection pool. The distributed architecture solves the application and business issues of storefront by providing scaling, millisecond response times. They can innovate faster due to the loose coupling and the reduced blast radius for changes. The loose coupling also leads to less regression issues. Now that we have migrated into distributed architectures, I am going to talk about how you can manage the complexities introduced due to the distributed architecture design. We have multiple microservices in the new architecture, and these microservices run in their own process and have their own data stores. The microservices are communicating over network and they are no longer making in-process calls. So the interactions between the services can be synchronous or asynchronous. The data is also distributed. So I'm going to talk about the service interactions, data access across the service boundaries, and how you can aggregate the data from the backend and from the front end. Let's consider the order and inventory microservices. If the order service makes a synchronous or blocking call to the inventory microservice, it results in a tight coupling between the services, as the order service should know about the inventory service and its interface. This results in configuration coupling, network and contract coupling. It can also result in the timeouts and cascading failures if inventory service times out for some reason. If the synchronous call is required by the use case, you have to consider whether the order servers may be retrying the call many times. And imagine if multiple users are retrying the same call. This can block the threads due to the timeouts and can cause entire application to go down. In these situations, it may be pointless for an application to continually retry an operation that's most likely going to fail, and instead the application should accept that the operation has failed and handle the failure. The solution here is to use the circuit breaker pattern. This pattern can prevent an application from repeatedly retrying an operation that's likely to fail. It improves the reliability of the system. When using the circuit breaker pattern, there is a circuit breaker object that routes the call from the order service to the inventory service. If the inventory service times out, the circuit breaker can detect the timeout and track the failure. If the timeouts exceed a specific threshold, the application opens the circuit. Once the circuit is open, the circuit breaker object does not route the calls to the inventory service. It returns an immediate failure when the order service calls the inventory service. The circuit breaker object periodically retries to see if the calls to the inventory service are successful. When the call to the inventory service succeeds, the circuit is closed and all further calls are routed to the inventory service again. In the additional resources section of this talk, I have provided my blog post link and the link to my last year's summit talk where I dive deep into the circuit breaker pattern. When the use case does not require synchronous calls, the better approach is to use the event-driven architecture. When using event-driven architectures, the services communicate through events and result in loose coupling and a highly reliable system. The events are put on a queue or a bus, and the services listen to them and react to the events. Cascading failures can be avoided by using event-driven communication between the services. Here we resolve the issues caused by synchronous calls. Next, I'll talk about how you can set up workflows between the services. As microservices grow in complexity and the work is distributed across multiple independent services, you may want state management, orchestration, and increased failure handling. You may encounter use cases where you have to execute multi-step workflows within the microservices. For example, when the customer places an order, you may also want to add the item to the cart and log the inventory. AWS Step Functions provides workflow orchestration when repetitive, parallel, and conditional executions and wait states are required. So if the placing of an order needs an item to be added to the cart and inventory to be logged, it can be orchestrated through AWS Step Functions. Here we are using the parallel execution feature of the AWS Step Functions to implement the required workflow. Step functions can also be used for retry with backoff, conditional execution, looping, provides nested workflow features for more complex requirements. This concept can be extended to implement the Saga orchestration pattern, which is used to preserve data integrity in distributed transactions across multiple services. In the additional resources section of this talk, I have provided the links to my blog post and my summit talk where I dive deep into the Saga orchestration pattern. Let's move on to how the services can access the data owned by other services. We saw earlier that the microservices own the data in their data store. As you all know, database dependencies cause close coupling between the services. Accessing the data directly can lead to data corruption and cause regression issues. Microservices should communicate through API interfaces and should not call the data store of the microservices directly. If the order service needs information on an item, it should call the inventory service which provides item details. Order service should not query the inventory database directly. Direct access of data owned by other microservices can actually lead to regression issues. What if the team owning the service decides to change the database schema? It will break the other services that call the data store directly. When accessing the data through API interfaces, it's less likely for a regression issue as the APIs can be versioned. Now we see services are owning the data. Next I want to talk about data aggregation. You can aggregate the data in front end or through back end. To aggregate the data on front end, you can use the AWS AppSync service. It is a managed GraphQL service that allows you to combine the data from one or more data sources with a single network call. GraphQL is a query language for APIs that enables developers to query and manipulate data from multiple data sources and other APIs. So AWS AppSync can be used for data aggregation from front end. Next, I'll talk about data aggregation in backend. Microservices own the data in their own data stores. Frequently, you may need to aggregate the data and provide a consolidated view for reporting and other application needs. Different use cases may need different read formats. Reporting may need a relational database format, and UX may need a cache for fast access. Services that scale to millions of transactions per second may need a NoSQL database like Amazon DynamoDB that scales accordingly. So if you need to aggregate the data and project into different data formats, you can use the command query responsibility segregation pattern. This is commonly called the CQRS pattern. CQRS pattern is usually implemented along with event sourcing pattern. Event sourcing stores a time series of events in an event store database. This event store is the single source of truth. A projection of data can be reconstructed by replaying the events in the event store through an event processor. The RDS processor lambda function contains the logic to convert the event stream into relational database format. We can create different formats using different event processors. If you see here, the right side is called the command side and the read side is called the query side. The CQRS and event sourcing patterns allow you to separate the read and write operations for your data store. This is particularly useful when there is an imbalance in the read and write access patterns of your data. You can also use this pattern to create different formats of read data stores based on the use case of the consumer. In today's session, we spoke about migration into microservices architectures and how Strangler Fig pattern helps to minimize the risk. We also saw how you can use domain-driven design to identify the microservices. Once the services are strangled out, we saw how to manage distributed complexity, and we also had a quick look into the circuit breaker and CQRS patterns. So that brings us to the end of the session, but I have a lot more resources that you can refer to. To dive deep into Saga orchestration, circuit breaker, event sourcing and CQRS patterns, you can refer to our blogs and summit sessions here. We have implementation for some of our patterns in our AWS samples GitHub repos, and you can refer to them. To learn more about AWS services, you can visit skillbuilder.aws. We have over 600 free digital courses and hands-on labs. You can learn at your own pace, and when you are ready, you can take the AWS certification exams to showcase your expertise and grow your career potential. And with that, I would like to thank you again for taking the time to listen to this session. I really hope my explanation will help you apply the patterns to your own distributed applications. I just have one final request for you, and that is to fill in this session survey. It will only take a minute of your time, and it really helps me to know what you thought of this session. And I hope you really enjoy this rest of AWS Summit.